Hey guys, welcome back to AlgoYogi. We are doing tree series right now. Our next problem in the list is validate binary tree nodes. Let's visit the problem on LeetCode. So you have n binary tree nodes numbered from 0 to n minus 1, where node I has two children, basically left children I. So there are two arrays they have given, left child and right child, and the value at each index in both of these represent the left child and right child of the node basically at that particular index. The index is a node. So at 0 index, which you can see in left and right, the left child of 0 is 1, right child of 0 is 2. Right? So what we need to do is we need to return true if and only if all the nodes form exactly one valid binary tree. And I think given we have the number of nodes and the left child array and right child array, then we can only form just one binary tree, because otherwise what's the point of giving right child and left child and right child? So if node I has no left child, then left I will be equal to -1. So basically for using the value none, so see 1 does not have any child, so at index 1 in left child and right child the value is going to be -1. Okay, let's understand it in detail and find out the approach, how we're going to actually code up the solution. So I have taken first example here where we are given the number of nodes is 4. So we will have basically 4 nodes starting from 0 to n minus 1, which is 3. So this is the set of our nodes. Now we need to return if and only if we can form using all these nodes and the left child array, right child array, only one particular binary tree. And there might be a case where it might be creating a loop, and loop I mean this. We don't want that because that will basically be a cycle, and trees are not supposed to have cycles. So we will have to maintain some visit set and find out if we are not basically visiting some node again, and so that will basically be a case where we return false. Now other than that, let's get into the approach, how we're going to solve this problem. So I've taken the first example. Now you can see, let's create, using this information, let's create the tree by ourselves so that we understand the problem better. So we have 0, but I think we need to find, because we will not be given in our input that what is the root where we have to actually start. So root will be something that does not have any parent, right? So everything else will have some parent, right? It will be the root node that will not have any parent. So how do we find it? So basically this is left child group and right child group. If we basically combine all of them together and see which of the value from my index values, which basically the nodes, what is the value that does not exist in my either my left or my right. And if it does not exist, that means what? It is the parent node. It is the root node, right? It is the root node that the tree basically has. And that's where we will start our iteration to basically visit all the nodes and making sure that we do not have any loops or discrepancies. So we have a valid binary tree. And so clear that this whole group, left child and right child, is a group that those are the group of nodes that have a parent. And Now, since it's a tree, then there's supposed to be a root node, which we will find out later, but that would be the node that doesn't have a parent, right? So if I basically create a set of all these values, if I create a set of all these values, left child group and right child array, then the length of this cannot be equal to n, right? If it is equal to n, that means there is no node that is parent, or maybe every node is basically in some way is just, maybe 2 was pointing to 0. So that means that's not a valid binary tree. So we have to make that check. Then we have to find out our root. So we'll create a parent set that would be basically set of left child plus right child, and parent set length of parent set cannot be equal to n. If this is the case, then no binary tree. This is not the right binary tree. We'll return false, or we can just return false. What's next? Let's say it passes all these tests, then we find out root. And root, we will basically find out iterating over this set, this parent set, and we basically root will be equal to that I in 0 to n minus 1, which doesn't exist in my parent set. All right, we have root now. Now we have to traverse that, right? And once we are done traversing, if we did not find any cycle, we visited all the nodes just once, and my visited set is equals to the number of nodes, which is n, then I can simply return true. All right, that's it. That will be our entire solution, and time complexity would be big of n, and space complexity big of n, because we are storing and also traversing just all the number of n nodes. Maybe doing it twice, thrice, does not matter, but at the end of the day, the time complexity would be big of n. All right, let's code our solution. As I said, we have to create parent set. So that would be parent set, and I can just call it simply set, and I will append left child and right child. All right, now we have to figure out that there is no cycle, so that there is no node that's basically pointing. We need to find out that there is a root, and there will be a root, because there will be one node exactly that will have no parents. It wouldn't be pointing to any child, and that would be the node that does not have any index in 0 to n minus 1 that has any value inside my parent set. Okay, so first thing first, this is parent set. I want to remove -1. So I'll say if -1 in parent set, then I want to remove it. All right, so parent set dot remove -1. All right, because that will be in the array and parent set, and -1 is not a parent, right? It's the none value that, for the sake of convenience, we just added instead of adding none, because that wouldn't be part of 0 to n minus 1, right? So now if length of my parent set is equals to n, that means this is, we cannot create like we cannot validate this binary tree. There will be some case where root is being pointed at into the left or right child as a left or right child, and that will be case where you're creating a cycle, and we don't have cycle in a binary tree, so we return false from here. All right, now not fastly false. Okay, now let's find out root. Initially let's just call it -1, but we know we're gonna iterate for I in range n if I, let's just call it if I not in parent set, then we can simply assign the root that value, the index, and break out of this loop. So my root becomes index I, and I break out, because there will be one root, right? We just don't want to keep iterating, because we will, if this is a valid binary tree, then we would have just one root, and that's what we are trying to. We have already checked that this will exist, and we just want to find it out so that we can iterate over it, checking if there are any nodes making a cycle below in our left subtree and our right subtree. All right, so we have our root, we break out of the for loop, and now let's write our main function, which is depth first search, and that would basically be iterating over our entire tree. That will start with root, and if root is basically -1, which is none, then we return false. Sorry, then we return true, because that means it's a valid path that we have explored so far, following any of the group, basically right child or left child, and keep iterating their left and right child, and we came to a point where any child has -1 as their left child or right child, then that means that's the none value, and it's valid to have in a binary tree. It's okay to have like none nodes. All right, that means that they are leaf nodes. Okay, then we return true. But what if now, as I already said, we're gonna have a visit array, let's call it visit set, and that will basically tell us if we are visiting any node again. That means we have a cycle in our binary tree. So let's have a check if root in visit. If root is in visit, that means we return false. Okay, otherwise we just want to add this to my visit node. So visit.add, that's root, and here root it's not like basically a node, it's a value. All right, and then what else? Return DFS on left child of my root. Okay, and visit DFS of my right child of my current root. Okay, so this will basically change the value. So initially, if in first example, if you see, let me zoom out. In first example, we will start with 0, and that will happen. Actually, let me come out of this function, and that will happen. We will return DFS root. Okay, so that will start at 0. We start trading as 0. We check if root is -1, which it's not. So if root is in visit, it's not, but we add it to visit set. Then at left child root, 0th index in my left child, which is 1, we start exploring 1, and then we start exploring 2 in right child. And we keep going until it's either -1 or it's already in visit, so we return false, or we return true if we end up with a leaf node. And then we basically come out and return the final value. However, there is one more check we have to do, which is let's check if all the visited nodes are equal to n is equals to my length of my visit. All right, then I've already zoomed out. Let's try to run it, and I hope, I'm very positive this solution should work. And that's not what I wanted. I wanted to add them because I wanted to group the values. All right, this passes the test cases. Let's submit it, and voila, this is a really nice solution. Let's write down our time complexity that we have already talked about. It's going to be big of n because that's the number of nodes, and we are visiting each node once. Although we do have these different for loops, right? Like this one, finding out the root. However, they're not nested, right? So, and then this DFS, I know it's a recursive function, but at the end of the day, it just calls on each node one time. So that is basically iterating over each node once. So that is n times. So which makes the time complexity big of n. And space complexity, since we are storing all the values, all the nodes into our set, then space complexity would be big of n. All right, let's go. Let's fucking go. All right, let's go back to AlgoYogi, mark this problem solved, and we are very, very close to solving all the problems in the list. It just last maybe 10-11 problems remaining, and we did it, guys. Yeah, maybe like almost 30-40 problems solved. As I promised that each of these categories will have almost 50 plus problems. Some of them might have like 100 problems, and this year we are planning to solve at least 500. And once we're done solving 500 problems, then we are fucking ready to crush the technical interviews. All right, see you guys in the next problem. Please make use of AlgoYogi because it's a really nice way of tracking your problem, unless you just want to go to LeetCode and start like from anywhere, everywhere, and get lost. You don't want that. All right, see you guys later.